Hello. So today we're going to talk about laser cells and the power requirement. And so this is given by the mass of the spacecraft times by the speed of light times the acceleration over 2 times the reflectivity, where the mass includes the payload plus the cell plus any structure. And so let's start off with a nice simple example of a 1 kilogram spacecraft, which includes all these components, a reflectivity of unity, and acceleration of 9.81 meters per second squared, which is what we call G0. And so the power required to push this cell will be 1 kilogram times by 299,792,458 meters per second times by our acceleration 9.81 meters per second squared, all divided by 2 times 1.0, just to make it simple. And this comes out as 1.47 times by 10 to the 9 watts, or 1.47 gigawatts to push a 1 kilogram cell at 1 G. Just to show some other examples, if we had different masses, so different masses in kilograms, so let's do 1 kilogram, 10 kilograms, 100 kilograms, 1,000 kilograms, which is 1 ton. And so calculating the power requirement for these systems in gigawatts. For the 1 kilogram cell, as we know, this comes out as 1.47. For a 10 kilogram cell, we've got 14.7 gigawatts. For 100 kilograms, 147 gigawatts. And then for 1000, we've got 1470 gigawatts. So these are useful examples to show what kind of power requirement for pushing spacecraft to these masses. We could go higher. We could go to, for example, 10,000 kilograms, which is 10 tons, and the power requirement will be 14,700 gigawatts, which is equal to 14.7 terawatts. So as you can see, the power requirement is a strong function of the mass of your system. Now let's consider something a bit more interesting. Let's say we were designing an interstellar Voyager probe to be sent on an interstellar journey, and it's powered by lasers. Now the Voyager probes had a mass of around 800 kilograms, so we shall adopt that. And instead of a reflectivity of unity, we'll assume a conservative value of 0.7, and the distance we're going to is 4.3 light years. And let's say we want to do it in 100 years trip time. That means that the velocity we need to achieve is given by 4.3 light years divided by 100 years, which is about 0.043 c, 4.3% of the speed of light, which is equivalent to around 12,900 kilometers per second. And let's say we're going to push the laser not at 1g. The laser push is going to be at an acceleration of 1/10 of g, which is 0.1 times by 9.81 meters per second squared is equal to 0.981 meters per second squared. So just under 1 meter per second squared. And the time taken for the push is going to be velocity of the acceleration as an approximation, non-relativistic, which is 12,900 thousand meters per second divided by 0.981 meters per second squared, which is 13,149,847 seconds. And we know that 1 day is equal to 60 seconds, 60 minutes, and 24 hours. So if we divide this by 60 times 60 times 24, then the boost time is approximately 152.2 days. That's how long it would take to accelerate the SAO. And then the power requirement pushing this SAO is 800 kilograms times by the speed of light times by 0.981 meters per second squared, the acceleration, divided by 2 times 0.7, which comes out as about 1.6805 times by 10 to the power of 11 watts, or 168.05 gigawatts to push our Voyager-like probe, and 168 gigajoules per second, which is what we're dealing with, multiplied by our push time, which is 13,149,847 seconds, which is also 152 days, and this gives us 2.209 times by 10 to the 18 joules. Or if we divide this by 10 to the 15, we get an energy requirement of around 2200 petajoules for our Voyager-like laser SAO probe. Now, to put this into context, we can think about cost of such a probe. And so we can compare this to, for example, the US global energy consumption in 2024, which was of order 10 to the power of 20 joules. And if we divide that by 52 weeks, we get around 1.92 times by 10 to the 18 joules per week. And what's interesting is that this is very similar to what we computed for our laser cell requirement, which was around 2.2 times by 10 to the 18 joules. So in other words, our laser cell Voyager-like probe would require the equivalent energy consumption of the US in a week. That's it.